Are people wanting to carry on? Are you doing interpretive stuff or doing other stuff, or do you want to carry on and do a little bit more? Or? Cool. Oh, so you've been recording the whole time. So I've loads of me faffing. So the next example is kind of the more complete example, and it's from section 2 of the book. For me, this is like the main highlight of chapters 1 and 2, and it's this creating a language of pictures. So it's a deeply embedded language, and so it's a DSL, and it's a deep embedded in the sense of it uses features of Scheme, or in our case Clojure, as a means of combination of the language that you build. So I think I've got a separate rant about people doing DSLs for like configuration management and stuff, and how I think people should use like deeply embedded languages. So the means of combination, etc., are, for instance, Ruby's, or for instance, Clojures, rather than, you know, a bit like if you've ever used Ansible and it uses YAML, and YAML isn't a programming language, but then they have to do iterators, and they have these Ginger templates embedded in them, which kind of makes sense if you know Python, and it's all a bit of a mess, really. But that's a separate rant. Videos are available. So how to describe Escher? So this picture's called Square Limit, and if you look at the picture, you can kind of see, well, it's the same image, kind of shrunk, rotated, moved around, etc., and it kind of goes up to the limit, actually, as you can see. So we need a language for describing pictures. So we're going to build up a picture language. It's going to be in Clojure. So our first picture is called George. Can't remember why. Don't think it occurs in SICP. I don't know where I picked it up from. I've over the years looked at loads of different references and different universities given versions of SICP and stuff. So I can't remember why I named him George years ago when I first did this in JavaScript. So if we say call the function draw, and then say beside George. So George is our picture, beside is a function in our language Clojure, and draw is a function inside our language Clojure. But we can say draw George beside George. Yeah. So draw George beside the flipped horizontally version of George. So we start building up a way of talking about them, and then we've got this function below, which is beside George, flip horizontal George, and then below George, flip horizontal George. Actually, I'm thinking of, this is a little aside, I'm thinking of changing this to be above, because I changed it from the book so that you had a visual cue about where the pictures were going to be. So the thing that's here is on top, the thing that's here is underneath. That's a different order to the book, I believe, which causes a problem in a sec. So you're going to get a slightly incorrect version of the picture. But just to know, and the reason I wanted to do it like this is obviously a visual cue, because it becomes quite hard. That's on top there, so that's on top in the image. But the relation below, I think the better name would be above, as in we're saying this is above this. A bit like less than, we say less than 2, 3, and you're saying that can be in the middle, and it's this thing that's less than that thing, yeah? So I think that's this function. If I'd have had more time and not built that interpreter earlier, this would have been how I spent half an hour. So draw the rotation of George. Rotation just flips him 90 degrees clockwise, and if you look, it's kind of kept the same frame. So George is squished a bit into this frame, and I'll talk about frames in a minute. So generating new pictures from old. It's a deep embedding. So we can just use repeated function application. So because the rotate is a function, it's a function in Clojure, so we can rotate the rotation, and we get 180 degree rotation. We can rotate the rotate of it and do 270. And we can define below in terms of other things we know. So we've got below, we've got rotate, we've got beside, and you can then, that's enough to actually do a function that does below. The reason is, when I originally gave a version of this talk in JavaScript a while ago, I described all the code and then showed the picture. Now the goal is basically, there's just enough code for you to understand it, but there's gaps, and there's a project on GitHub which you may have already downloaded. Your job is to fill the gaps. So new pictures from old, right split. So we say, and again, below and beside might be wrong here. This is picture stolen from the book, stolen, borrowed, lifted, edit that out in post. Taken from the book. then so we define the right split of some picture and some number, and then we recur. If n is 0, it's just the picture. And then we say the smaller one is the right split of the picture, and we're going to decrement that. So we've got our, our base case for the recursion, and we say we're going to draw beside the picture, below, smaller and smaller. So smaller appears twice, yeah? So that's a right split, which isn't affected by my below above bug. So draw the right split of George for, remember, we're decrementing constantly, and we're drawing 2 of them, so it's going to go down in 2s, and then we started with 4, so we get 1, 2, 3, 4 extra Georges, and we're going out 2 each time. And whoever it was, and I think the picture itself might be from the book, I think, they've done it so that when you draw George on top of George, his head kind of becomes his legs, which is kind of like a nice effect. It's not quite useful, not quite the symmetries that the Escher tiles expect, which is an interesting exercise for the reader, is what is the sort of optimal symmetries. He does the fish, and you can draw a fish. I've got examples where somebody has sort of gone through and figured out what is the ideal fish for the symmetries that you need. Here's where what it says here doesn't match the picture quite, because remember I said I'd swapped above and below to onto the visual cue, so excuse me. But I've tried to make it a little bit clearer. This concept, corner split is the up split of the right split, and then the top left is beside up up, so this is up. So we're using the fact that in Clojure, left bindings can see the previous one. So I say up is the up split, right is the right split, top left is beside up and up, which is actually here. Yeah, top left here. Bottom right is below right right. Bottom right is this one, below right. And right was the right split, yeah? Bottom right, corner is the corner split, and then, so corner split's going to be here. So like our corner split we just saw, so it calls itself recursively in here. So basically it's going to head off this way. Now, here's where we get a bug. Actually, in my version, it heads down this way. Because I wanted a visual cue about the order of things in my below function. But you see the idea, right? We call it recursively. We're drawing the original picture, identity. We're doing the up split here, side by side. We're doing the right split here, side by side. And we're recursing into this corner. So hopefully that's clear. That's the identity. And we're recursing into this corner. But 2 copies of right split, or top split, whatever. 2 copies of right split going that way, yeah? So we built up this grammar of pictures. Sorry, if I just retrieve my drink. But we haven't sort of learned how to draw anything yet. We're just relying on the fact that this draw function exists. And that's kind of this idea of hierarchies or whatever. You could draw these pictures and just take draw as a given, right? If you want to combine this picture using all of the functions we've created and create your own functions, you don't have to care how draw works. And it's that stratified design is one of the sort of main lessons of the book, is you can treat draw as a primitive now, but if you do care about it, go and look at it. It isn't, it's sort of, stratified, like layered. So, assuming we've got another picture type, you can say a quartet, and again, below, beside, P1, P2, that's these 2. Beside, P3, P4, that's these 2. So we've got George, box, that's the fact that the box hasn't got a right boundary is an artifact of the drawing, because you're drawing on the bounding edge, and so that should be a box. And then the man picture, and then the Bruce picture there. So there's another image type. This is created out of lines. This is created out of images, and draw doesn't mind. So one thing that is I think really really nice about this. I'll talk about that in 1 sec, sorry. But then we've got this higher order procedure. So just before this section of the book, you spend a lot of time talking about higher order functions. So in order for things to be higher order functions is when functions can be the arguments or return types to functions, and this is this idea of like first classness. So functions are first class in this. You can store them in data structures, you can name them and refer to them, but also importantly, you can have them as arguments and return values for your functions. So we've got a function called square of 4, which takes 4 pictures and returns a function of a picture, which then does those things. So this is a picture transforming function. So this function takes 4 things and returns a function of a picture, which then puts on top, beside, top left is a transformation of a picture, top right is a transformation of a picture, so it could be flip, it could be identity, it could be whatever. So a transform in the picture and with the top left transform in the same picture with the top right transform. So you give it 4 transforms and it returns a function that takes a picture and transforms that picture. Does that make sense?
So you're supplying functions to it, rather.
These are transformation functions, yeah. And you can tell because look what we do with them, we call it on P. So flip horizontal P, rotate P, yeah, it's a good question. So we know, we can infer what these things are by the way they're used, right? So yeah, it's a great question. You're passing in functions that transform pictures, and what it returns is a function that transforms a picture. Yeah, so this takes four transform functions and returns a picture transforming function. Yeah, so it's that Clojure idea again, because each of these will transform a picture, right? And together they return something that transforms a picture. So 4 operations, oh there you go, I even wrote it. 4 operations returns a function of a picture that draws the picture transformed by them, each in a quarter of the frame. I'm not so sure I'm happy with that prose. So square of 4, identity, flip vertical, flip horizontal, rotate. So identity, flip vertical, flip horizontal, just that way, and then rotate, right? And then on the George picture, so we're assuming George still exists. We're assuming that draw exists. And yeah, we still don't know how to draw anything. So what is George here? And you'll be pleased to know George is a function as well. So this is the sort of collision again of what counts as data in our language and what counts as like code or procedures. So George is also a function. So we're definitely in higher order function territory here because this is our function that takes 4 picture transformation functions and returns a function that transforms pictures, which are themselves functions. Pretty sure I said that correctly this time. So we still don't know how to draw anything. So we've got this draw function that seems to be called on a picture, which is also a function. So what is that doing? So first, a little bit of, what do you call it? Housework. In order to draw a picture in a thing called Quill, which is a sort of Clojure binding on processing, a Java library, you just need to instantiate a sketch. So def sketch, I'm calling it Escher. It's got a title on the window bar. Every time I draw, I'm going to call this draw image function, and I want it to be a size, width, and height. Should have probably put a refresh rate in there. I think by default it does it every 0.1 seconds or something, which we don't need because our image isn't changing. It's drawing the same thing again and again. So that's a thing to add into your project in a sec. So when we use Quill can draw lines. So in the Quill namespace, there's a function called draw, which can be called a few different ways. Either you give it a pair of points, or you give it 4 coordinates, or you give it 6 coordinates. So we're going to do the 2-point version. So it expects 2 points, which are just pairs. Vectors are pairs of coordinates. So we can define, and this is again why one of the lovely features of Clojure as against scheme, we can do destructuring here. In the scheme version, we're constantly saying, give me the x value of this vector, give me the y value of this vector. I'm going to create a vector using the makeVec function with the x value of this vector, the y value of this vector. We can do it very neatly using Clojure destructuring, which is the first argument to our function is a pair, and we name them x1, y1. If you don't know Clojure destructuring, definitely look at it because it's beautiful stuff. And you can even destructure maps, you can do nested destructuring. So you're saying, I expect 2 arguments to my function, both of which are pairs, and I can name the contents of them, x1, y1, x2, y2. In order to create a new vector, I'm not, and again I'm comparing with the scheme code, but you've not necessarily seen it, but in the scheme code you say make vec, and then you pass in these pairs, and then you have to do get x of the vector, etc. So Clojure as a sort of expressing the idea much more succinctly, with the downside that you don't have the data abstraction in terms of saying, give me the x coordinate, give me the y coordinate. But you've got, the only thing it has to do here is it has to match. So it could be, it happens to be a Clojure vector. You could use anything that has n, where you can take the first and second. So Zach Tellman has some like efficient tuples and stuff like that that are backed. I don't know if they're backed by arrays actually, so I wouldn't say that. They're faster for small collections than Clojure's default vectors are. And an interesting exercise might be, well, if we do care about speed, this is a fast thing. Can we use something faster in here and still keep the nice? So do we have the data abstraction because the interfaces must be destructurable rather than, it doesn't have to be a vector. I hope that makes sense. And subvec and scalevec are left for you. So scalevec makes it longer in the same direction, which if you remember is sort of multiplying the components by the scalar. Line segments are just pairs of vectors. So it's just 2D geometry basically. Any 2 points defines a line in the space. So it's just a pair of vectors is a line segment. A path, because I wanted to draw paths, this isn't in the book, but it's useful. So I said a path from, this is the points we stop off at, returns a list of line segments. So if path goes from here to here to here to here, I want the line segment from here to here, the line segment from here to here, etc. So return a sequence of line segments is a path. And then there's this idea that data is code and code is data, and we always say that. And what people often mean is, well, my programming language is S expressions, I'm capable of implementing, so I'm capable of manipulating S expressions, I may or may not use macros. But what I really like about this, just like the Comp's car coulda example before, where what was considered to be a data structure, we implemented in terms of lambda expressions. Similarly now, what are the data in this, the pictures, are actually just procedures. So a picture is a procedure that takes the responsibility of painting itself, and what you do is you hand it a frame and say, draw yourself in this frame. So we need to know what a frame is. So again, unfortunate borrowing of the image, 0, 0, and then a vector, and then a frame described by it. Turns out in processing, Canvas, loads of other libs, the 0, 0 point is actually up here, and y increases down the page. So this is a somewhat confusing diagram, but you've got, the key idea is, there's a vector to the corner of your picture, and there's 2 vectors that describe the edges of it, and that's the frame you're going to draw in. So bottom left corner is here in this instance. In the case where we're coming in here, it would be here, right? So I've got some pending work to draw myself some diagrams here. But we're actually going to, again, take advantage of Clojure's built-in map type. Again, the scheme has get origin, get first edge, get second edge as functions described on a list structured data, whereas we can say, well, call the keyword and fetch out the origin. And if you remember from all of the Clojure protocol stuff, you can actually replace that with a def record if you want it to be faster as well. So it doesn't have to be a map. It just has to take that interface of, can I call it with the keyword and get the value out? And again, a record would be faster. So we're losing some of the data abstraction, gaining comprehension and brevity, but also if we do want to replace it with something faster, and then get that data abstraction, the only thing is it must accept the key as a function and return the thing we're interested in. So is that okay? Do people know what like records are, def records and stuff? Okay, cool. So we lose some data abstraction because SICP hides them all behind getters and make functions, but we haven't lost the power of switching out the implementation. We've got another constraint where we must honor that sort of keyword interface. So our first picture then, frame painter just draws the frames. So you give it a frame, it draws the boundaries of the frame. Does that make sense? So we say the corner is add E1 and E2 to the origin, and yeah, so so it's the far corner, isn't it? So we say, what's the far corner? We know where the origin is, and we connect the origin to the far corner by going to each edge. Does that make sense? So the origin, and then add to the origin E1. so that's, say, the bottom edge. Add the origin E2, that's, say, the left side. Add E2 to the corner, that's, say, the opposite side or whatever. So we just go in each of the 4 things. We're saying there's the origin, and then there's the corner, and we say connect E1 to the origin, E1, and then E1 from the other edge goes the same direction. Does that make sense? So we say, and we do some Clojure destructuring again here. This expresses the intent much more succinctly. We say fetch out these keys, origin, E1, and E2, from our one argument, which is a map. Again, if you've not seen the Clojure destructuring, it's great. And draw those 4 lines. So 2 of them start at the origin, 2 of them start at the edge of E1 and E2. So 2 of them start at the origin, right, going like this. 2 of them start at the edges here, going towards the corner. Yeah? And we're just drawing them. So that's one frame, that's another frame. And if we give the frame painter that, it will draw the lines. So there's what we've drawn. So we say frame painter, which is a function, takes a frame and draws it. Frame painter, which is a function, takes a frame and draws it. Yeah?
Is there any reason why you chose that order of implementation of the draw lines?
No.
Okay.
It shouldn't make a difference either, because they're actually...
No, it doesn't, but I'm just wondering if there's a choice way choosing to do it that way rather than doing it.
Every line is completely independent. So I say draw a line, it just draws it. It isn't that there's some context and I say draw a line now based on where you are. Draw a line now. It's not like turtle graphics. It literally is. Draw a line from here to here. Draw the line from here to here. So they can be done in any order, in fact. It's a good question. Because a lot of these turtle graphics-y type things do have context that's building up as you execute stuff, right? And you definitely could write a function like that in there, where you had, some kind of position and you were doing things relatively to that. That isn't what we're doing. We're just saying draw the line from this point to this point. That's an excellent question. Any other question? Cool. So we draw those 2 frames. Now we need to start drawing real pictures inside them. So, add vec. I've got that's 2, the number 2. Excuse me. So more than 2 arguments. So add vector is not variadic. We can only add 2 vectors now. It'd be really nice if we could add an arbitrary number of vectors. So that's an exercise. Segment painter takes a segment list, returns a function of a frame, but remember that's what a picture is. A picture is a function. It takes a frame and draws inside the frame. Segment painter takes a segment list and returns a picture that then says, so I've got this map function. So the map is the frame coordinate map of the frame. Weird, don't know what that means. Do sec, that's our sort of side effecting thing in Clojure, right? Same bindings as the for macro. You say where it starts, where it ends in the segment list, yeah? Segment list is a sequence of pairs, and we're destructuring again. This has let bindings similar to before. I don't know where everybody is, so I'm saying things that loads of you will know, and some of you might, and I find it hard to decide what to say and not to say. So we say draw the line that starts at the mapped version of the start and the mapped version of the end. That's the only strangeness. If we didn't map it, you'd know exactly what that was doing, right? It'd be a list of segments, and you'd just be drawing lines. Well, you've got this frame coordinate map thing, and what that's doing is, the convention is, your pictures are painted in the unit square. So your vectors are all sized less than 1, and then you draw them in the unit square, and then what frame coordinate map does is blows up your drawing into the frame. Does that make sense? So you're not just drawing a list of segments anymore, like we did on this one. Like we did that one, we just literally did draw the lines, didn't we? And we had the exact coordinates where we wanted to do. The pattern is now, we draw our drawings in the unit square, so all our vectors are not normalized, because then it'll all be 1, but all our vectors are in that scale. So the picture we want to draw, if we want to draw a diagonal, say, we go from 0, 0 to 1, 1. Yeah? If we want to draw the box, we go from 0, 0 to 0, 1 to 1, 1. Yeah? And then whatever we draw in that circle gets blown up into the frame, and the thing that does it is this frame coordinate map. So we're adding the origin, always, and we're scaling x along E1 and E2. This is complicated, but you don't have to understand it straight away now in order to know what's going on. Just the idea, we're taking drawings inside the unit square, blowing them into our frame by using the scale functions we've created. Have a think, and there you go. So the diagonal, segment painter from 0,1 to 1,1, like I said, that's this. And then also I've drawn the frame painter as well. So this is the diagonal painter, diag, of frame 1. This is the frame painter of frame 1. So you see I've drawn the diagonal there twice. This is 0,0. This is 1,1, because y increases downwards in this drawing framework. Is everybody clear what's going on thus far? Cool. Oh, how tight is timings for the 9:30?
Tight.
Is it?
Well, we can go to like 9:45.
Okay. I don't need quite that much, but I don't know if it's going to cause you pain.
Keep going, that's great.
Cool. So our draw function now, so we keep saying draw these pictures, draw these pictures, draw these pictures. But we also know that pictures are functions that you pass a frame to. So draw is just a function that takes a picture and calls the picture, i.e. draws it on the whole window. So the whole window is just a frame. The draw function just calls the picture on the whole window. So all the draws you saw earlier are, we'll take that picture and just pass it as the frame, the whole window. So that's how we were able to draw the big picture earlier. I hope that's clear. Making new pictures from old. Here's a tricky one again. Probably won't understand it on first pass. Oh, in fact, I haven't even finished my explanation. So this picture transform, basically, you take a picture, an origin, an edge, and an edge. It returns a frame, which is another picture, right? A function of a frame. So it's a picture transformation. It takes a picture, takes an origin, takes two edges, and it does frame coordinate map on the frame again. Well, that's this frame, and it says it makes a new origin, which maps the origin, and it says call picture on not on the frame past, not on this frame. Call the picture on a new frame made by transforming this with the new origin. And what that has the effect of doing is manipulating the frame inside the frame, if that makes sense. So I think that isn't a very good explanation, actually. So you pass it in, an origin and two edges. This is relative to the frame. So if you say like -1 or whatever, then it starts heading that way instead of that way, and it will flip it. So you have to think, probably go through one by one and decide. Maybe a concrete example in a second helps. So transforming the picture with, instead of so this is, remember the order we're calling them. So it's a picture, new origin, edge 1, edge 2. So the picture, but the origin, instead of being 0, 0, the origin's 0, 1, so the origin's here instead. And then the new edge is 1, 1, so that's actually here. So it's the picture's starting here and going here. So it is why it's flipped vertically, right? We've said, don't draw the picture in 0, 0. Start at 1, 1. Sorry, start at 0, 1. Don't proceed along the bottom, i.e. like from 0, 0 to 0, 1. Go towards 1, 1, and then go towards 0, 0. So you're saying from 0, 1. I should probably so from 0, 1, which is here, instead of here, right? Y increases downwards. And then go to 1, 1, which is here. So that's your new bottom. And your new top, your new other edge, is the edge to 0, 0, do you see? So instead of starting here, and Y going down, and X increasing, you start here, and you're going that way. So it has the effect of flipping vertically. It's a strange, do a few sort of concrete examples, and draw the vectors, etc. I need to add a sort of more explicative diagram there, rather than waving my hands, but I hope some of you got that. It's not a problem if you don't, because flipping horizontally and rotating can be done using this transform thing, and a trial and error will give you a good intuition. And that's a great thing about having fast feedback in Quill, as you see in a minute. If you get it slightly wrong, you can develop an intuition for it anyway. So this is now, beside the function that we used before, two pictures. So it says the split point is 0.5, 0, and there's a left picture and a right picture, which is transform picture, but don't draw it started at 0, 0, end at the split, i.e. end in the middle, and then take it to 0, 1. So it's the full height, but it's only half of the width. So this is a new frame, right? And this is a picture that draws only in the right-hand side of the frame. Does that make sense? So we said start at 0, 0, as you did anyway, but end at the split point and end at 0, 1 as you would. And then you return a function of a frame which says draw the left in the frame, which remember takes the frame but just draws in this bit. Draw the right, which again takes the frame but just draws in this bit. And you can do below similarly. So we've got beside and below. I've got 4 minutes, and I reckon I can do it. So there's a different picture type. Say Quill, as well as drawing lines, can also draw images. So you say, well, how do I get an image painter? And the answer is, well, Quill has this load image function. It takes a relative path, which is all set up for you already. If you call image painter on this image, then you can say, well, put Bruce in frame 1 like we did before, put Bruce in frame 2 like we did before. And as an exercise for the reader, I thought my solution was very nice in terms of doing nested destructurings. So fetch the origin key and name its parts, fetch the E1 key and name its parts, and then do something nice here. And I'll give you a hint at how to fetch the width and height of the actual image, so you've got to do some scaling. That's quite an interesting. There's a load of different Quill transforms, rotations, etc. If you've done any 2D stuff before, it's going to be easy. If you've not, it's hard. The order of the transform command is different than canvas. So I've previously done this in JavaScript and HTML5 canvas. The order's different, which befuddled me for quite some time. If you want to save an image from inside canvas, just call q.save. And then if you draw the square limit that we defined before of our new image type, it doesn't really do what we want, which is flip and rotate, etc. And if you take a tile that I've given you, which is the so-called angels image tile, you can get something like, it's not angels, it's bats, isn't it? There's also an angel tile somewhere. But then you do have the sort of effect we're after, some references, and I'll just show you very, very quickly how Quill works, how it looks. And then I'll finish just on time, which will be nice and rare. So, if I eval this, it should... Oh. Sorry. I actually have an environment to eval it into. Don't cheat, you can see my solutions now. So there you go, it's drawn, and as I said with Quill, everything is evaluating every, I think, 0.1 seconds by default. So if I go to I've said the draw image function is what gets drawn, and I've commented out a few things that I thought might be useful. So if I change this, where's actually what's getting drawn? Oh yeah, there you go, so square of 4 was getting drawn. If I comment that out, and eval it, see nothing gets drawn. If I say, so it's a really nice way to get like a bit of an intuition for how the functions and transformations and that work. This project is called Escher. It is on the SICB Distilled GitHub. I hope you are all part of the GitHub now. If not, sign up tonight and I'll make sure you're added. Final thing, there's some instructions in terms of what functions need completed and in what order, etc. So this is a sort of a more fully formed problem set from SICB Distilled, and as you can tell, the slides are a little bit more complete than my the description of the interpreter was perhaps before. And also, I'm really tempted to do this hyperbolic one at some point, because there definitely will be a way. Any questions? Well, thanks again for your indulgence. Thanks for all listening. Thank you.
Cool. Well, thanks everyone for coming. Said at the beginning, we're going to do this again.